Hi, hi Robert. How are you? Nice to see you. The people that will be joining soon, just let me think.
Hi, my mic was off.
So, thanks for being here. It's a pleasure to have you in the bootcamp and be able to have a talk with you on these topics of GPU acceleration for zero knowledge proofs. Um, so I think more people will be joining shortly, but if you want, we can begin um, as soon as you like. And if you don't mind, we can record this talk and later share it for other people to see it.
Of
Or
course, of course.
okay,
We can wait a little.
okay,
You tell me when we when we should.
okay. I'll uh, let me. We can wait for 4 minutes or something. And, um,
In the meantime, I can try to show my screen.
okay.
When I start it as a slideshow, do you see it as a
Yeah, yeah,
full screen?
perfectly.
Okay, okay.
Awesome. Well, some more people have been joining in, so that's great. Um, so if you want, we can start. It's as I was saying, huge pleasure to have you here and talk with us about GPU acceleration for CKPs. Um, it's wonderful to have people from such an amazing team and that we have like a close collaboration. So please welcome and thanks a lot for joining us.
Okay, thank you for inviting me. Happy to be here. Um, uh, as you can already see, um, this talk is about is basically an introduction to GPU acceleration applied to ZK cryptography. Um, I am an applied cryptographer at Metro Labs, and I am in charge of implementing all the GPU uh, acceleration. It's mainly about accelerating our provers. Um, yeah, so we can dive into it. First, the agenda, what this talk is about. First, I will review the uh, options we have in terms of hardware we could use um, to calculate the proofs and what they offer. Then I will go a little deeper into comparing CPUs versus GPUs. GPU is my expertise, so that's what we will focus on later, but I also want to give you some comparison between GPUs and CPUs, just to see some what's possible, what performance numbers we can get from those architectures, and yeah. Then I will talk little about NVIDIA's GPU architecture, and after that, we I will show you a little very simple CUDA program, you could say, um, and explain a little bit how we do the programming in CUDA. And yeah, you will see a piece of code that's doing some simple calculation. And the last part I called anatomy of a GPU prover. This is taken from a talk I have had at in Gonyama's uh, ZK GPU masterclass. Uh, just reduced a little bit, and it's this part is about our prover, our newest prover, and I will talk a little bit about how it's constructed, what kind of operations we do there, what problems we had with it, what solutions we came up with. Yeah, and that will be it. So I think okay, yeah, and um, should anyone have any questions, please ask right away. We can have a discussion. I think we have 1 hour reserved, so let's use it. Okay, let's go to the hardware options. This is full of acronyms, as you can see. We have CPUs, GPUs, FPGAs, ASICs, and I also included SoC. I will explain each one. CPU stands for Central Processing Unit. Each computer has one. So this is basically what people use in general. Um, doesn't We have all the tooling and libraries and whatnot. So yeah, this is probably what majority of people use for crypto or ZK code, and all the other options are more about getting more performance than usually you can get out of a CPU, but we will look into that in a little bit more detail. The second one is GPUs. The G stands for graphics processing unit. GPUs started as basically devices for graphics, purely for graphics, and for a long time they were used only for that. But later people figured out that the shader language, which existed for writing graphics shaders, the small programs to do some operations on graphics data, those those same units and the same language could be used to kind of arbitrary computations. And first it was sort of just a hack, and then later people realized that this could be turned into general computation, and NVIDIA jumped on the bandwagon, and then they started to offer like the tooling and the language to do that. Okay, let's continue. Then we have FPGAs, which stands for field programmable gate arrays. These are a little bit more special than GPUs. These devices have kind of a mix of different units, stuff like digital signal processing units, lookup tables, flip-flop arrays, and the point is that these devices are sort of wired to uh, specific functionality. So you don't really program them with some language. They are not some general computation devices. It's more like you are wiring together different units, and you can literally wire together some gates, like logic gates, and this combined uh, basically leads to or produces some circuit basically, which is able to compute whatever you want. But the difference here is that if you want a different functionality, you need to rewire it, and it's not instantaneous. So it takes a short amount of time, but it's not something you want to do like constantly, like rewiring it, changing the functionality. Um, FPGAs are quite powerful when you can find a problem that suits them well. Um, Mostly stuff like streaming and processing data in streaming fashion. That's where they excel at. They are also usually not that intensive in terms of power usage. So depends on the problem. They are good at some stuff and not so good at other stuff. Then we have ASICs, which stands for application-specific integrated circuits. These are your typical chips with some uh, specific functionality, stuff like you find, for example, in Bitcoin miners. They are just for computing hashes, for example, and they are usually extremely efficient and extremely fast. Like we are talking. Maybe 2 orders of magnitude faster than what you get from GPU or FPGA. And then last category I'm chosen to list here is a system on a chip. These are mm, they don't exist yet, I would say, for ZK, but maybe later, where you basically bake together some general processing unit and marry it with some special like you could imagine a sort of a CPU, but it has a ZK coprocessor for doing, I don't know, modular arithmetics, for example, something like that. And back to ASIC and SoC, these two categories are actually not currently used in ZK cryptography because the pace of change and pace of uh, like how fast we are changing the proof systems and all the stuff around that, it's very high. And for ASICs, for example, it would totally not make sense to try to make an ASIC at this time, as long as we are changing all the algorithms all the time, because ASIC is to make an ASIC, it's a very expensive and time-consuming process. So we are talking maybe at least months, maybe a year, and I don't know, uh, could be millions of dollars to produce it, basically. So yeah, and SoC is kind of similar. So yeah. So right now we are mostly stuck with CPUs, GPUs, and FPGAs. Okay, let's continue. Uh, little bit of uh, comparison versus CPUs and GPUs. I won't go into FPGAs any deeper because that's not my area of expertise. So I focus on GPUs, but I want to compare versus CPUs where usually people start with, and so we have a little bit of an idea how those two compare. Um, so this is very high level image. On the left side we have CPU, and we see that let me try to engage. So this would be the CPU, and this would be the GPU part. DRAM, like the RAM, is kind of external to those two. Um, but on the CPU side, we can see that the actual, and this is too big actually. So the actual logic, which is doing for the example the integer operations, is usually just a fraction of the total area of the CPU, maybe 5 to 10% usually. Uh, Much of the area is spent with L2, like with the caches L2, L3, L1, and a lot of area goes into the control, and we will discuss it a little bit more later because CPUs need much more complicated control circuits than the GPU. And on the other side, we have GPU where the caches are a lot smaller, and also the control circuits are much smaller. So GPUs are a little bit less complicated in terms of the logic that they can do, and more area is spent on the actual units that are doing the computations. Okay. So this is just uh, some summary of the CPU, what we can expect from it. So CPUs usually have high single-threaded performance, which means they can clock very high, and single core can do a lot of stuff at the same time. Uh, it's quite complicated piece of hardware. Also, they can go high. They can clock very high. So you get a lot of performance from a single core. They have a complex pipeline um, containing all sorts of decoding and branch prediction, out of order, and superscalar execution. Superscalar means they can actually issue multiple instructions at one clock cycle. And they have also multi-layered cache hierarchy, usually nowadays 3 layers of caching. And what will be important to us is they have SIMD units. SIMD stands for single instruction, multiple data. And these units are uh, moderate in size. We will talk about it a little bit later again. And here is an example of the latest and biggest AMD server CPU. This was released just a few months ago, and it's a very big CPU, very massive, very expensive. But it's made of chiplets, 16 chiplets, 128 cores in total, 256 threads. So a massive beast, much bigger than your usual desktop CPU. Goes up to 3.1 or can maintain 3.1 gigahertz on all cores. you see the cache sizes. I want to go through this rather quick. 12 channels of DDR5 RAM, 4,800 mega transactions per second. And here is the calculation to kind of for the memory throughput, 460 gigabytes per second, and we will compare that later to a GPU. In terms of SIMD, um, those CPUs offer AVX 512 instruction set, which can compute, for example, 16 32-bit integer operations in one clock. So we get something like 6.35 tera integer operations per second. Um, Consumption by default 360 watts, and the price is very expensive, 11,900 dollars. That was the suggested retail price. Now GPU, it's a little bit different. We only have one clock for the whole GPU, so there is no kind of separate clocks for different parts of the GPU. Just one clock. The pipeline is rather simple, so we don't have any branch prediction or out of order execution or superscalar execution. We have only 2 layers of cache, and those are smaller. But what we have is very wide SIMD units. So the as we will see later, yes. So let me go further, and then we will see. And they usually have a higher memory bandwidth and potentially a lot higher. So here we have an example, and this is a gaming GPU, RTX 4090. So this is what you can buy in a store. It's the highest GPU, the gaming GPU you can get, but it's very powerful. Um, this GPU is connected through a PCIe bus to the CPU. Um, it's PCIe 4 generation 4 and 16 lanes. This I think gives theoretical speed around 32 gigabytes per second of speeds, because you have to somehow move data between CPU and GPU before you can do the computation. Then next we have 128 SMs. These are SM stands for simultaneous multiprocessor, and it's somewhat comparable to a CPU core. On these GPUs, we have 2.52 gigahertz boost clock. So that's how high it can usually boost. The clocks are not stable, so there is some variance. We have 72 megabytes of L2 cache, and that on board there are 24 gigabytes of GDDR6 RAM. I will skip that, but this calculation gives us the total throughput, and that's almost one terabyte. So that's already, compared to the biggest server CPU can get, it's already more than twice. And there are actually, and this is a gaming GPU. On the GPUs that are for data centers, on the latest one, you can go as high as 3 terabytes per second. So that's almost factor 10 in terms of memory throughput. And in terms of integer operations, we can do, one SM can do 64 operations per clock, And when we do the calculation, we see that's 20, roughly 20 tera integer operations per second. And when we compare that to, sorry, to the CPU, we've seen that that was able to do less than 7. So, you know, that's already more than factor of 3. Again, and this is a gaming GPU, which costs $1,600, so much cheaper, and can do a lot more computation than the biggest CPU. So and so from this comparison, we can see why GPUs have the potential to deliver a lot of performance for, you know, we care mostly about price actually, because um, when we do ZK proving, um, those proofs are usually highly parallelizable. So we can throw a lot of hardware at the problem in parallel. So what we really care about, for example, concretely at Metro Labs, we are renting GPUs from Google Cloud, and so we care mostly about the price per performance. Because, you know, we can scale how many how many GPUs we need, 100, then yeah, we can get 100. It's all about the price, because in the end, that's what determines the price per transactions, basically, when you count it. Okay, let's continue. And this is something actually something new. I think it's not released yet, but this is a solution from NVIDIA where they are pairing a ARM CPU with something like 72 cores with the newest Hopper GPU, and um, these two pieces of silicon are uh, on the same board and are connected with a very fast 900 gigabytes per second link, and they have a hardware coherency. That means they can each access the other's memory in a coherent way. So this is just an example where maybe in the future this might go. Although we as Metro Labs are actually going into the other direction. We are trying to avoid any data center grade hardware, and we are actually trying to go much lower in the specs, and I will talk about it a little bit later. But this is just an example of something that could be used because I think you had a talk with someone from Ingonyama like two weeks ago, and the issue they mentioned, one of the main issues you get when you try to do hardware acceleration on GPUs or on FPGAs, it's the same. It's the problem of transferring data from CPU to GPU and back. So that's a major bottleneck, and so you want to avoid that as much as possible. And with this new board, you are not limited by the PCIe speed, which is like 32 gigabytes per second. Instead, you have a massive link of 900 gigabytes per second, which, you know, kind of takes care of that problem. Okay. Now a little bit on the GPU architecture. This is a diagram of the latest Hopper chip, GH100. So this is the full chip, fully enabled. In reality, the graphics cards which contain this chip, usually some of the units are disabled because these are very big chip with very big area, and usually you don't get fully functioning chip without any flaws. Like during the process, the bigger the area, the more probable it is you get some flaw somewhere, and then the manufacturer can basically um, like cut off certain parts. So uh, for example, here in this chip, you would get 144 SMs if it was flawless, but instead of in a GPU, you only get 132 or something like that of those. So a bunch of those SMs are basically disabled because there are some flaw during manufacturing. Um, so I don't want to go any deeper than that. Maybe I mentioned that we see some memory controllers here, gigathread engine, which takes care of scheduling the work for these units, and then what we see here are 6 big blocks called GPC, GPU, I think, graphic processing clusters. Um, and they contain these TPCs, texture processing clusters, and each of those contains 2 SMs. And yeah, you have a bunch of those and a piece of big L2 cache. Um, when we zoom in into one SM, um, we have stuff like L1 instruction cache, and actually we have 4 schedulers which are kind of independent. You could compare it maybe to 4-way hyperthreading in terms of CPU, but it's not the same, but kind of similar idea. You have 4 independent schedulers which have their own execution units and can schedule work uh, independently. Uh, when we schedule work on a SM, uh, it gets broken up, and pieces of the work land in are like distributed across those 4 schedulers, and each scheduler has its own set of registers, its own L1, sorry, not L1, instruction cache, its own load and store units, special function units, its own set of floating point, 32-bit floating point, and 64-bit floating point, and int32 execution units and other stuff. Um, the idea is here, once the works is split, uh, I have to mention another term. It's called warp. It's a kind of a work of unit of work. Sorry, I think my mic died a little bit. Can you hear me?
Yeah, perfectly.
Yeah. Okay. Um, so the important part is that these schedulers, um, the work gets split across them, and the work, those units do not cannot migrate. So once they are on a scheduler, they stay there. Um, and these schedulers have a very big register file. So it's 64K registers per SM. And the idea is here that we want to have basically zero cost context switches. So you have multiple warps which are managed by the scheduler, and the scheduler can switch at zero cost between them. So basically, if one warp, let's say, is waiting for some data or some result of some instruction, the scheduler can just grab another verb and execute an instruction from that one. And so this context switch is zero cost because of this massive register file. You don't need to load and unload the state of each verb. Uh, the registers are basically split among the active verbs on the scheduler. Yeah, and so in this case, for example, we see that each scheduler has 16 integer units, so this gives you 16 integer operations per cycle, and you have 4 of those, so in total 64 integer operations per cycle. Okay, let's go to CUDA. CUDA stands for I have to remember Compute Unified Device Architecture, I think, but it's basically a term NVIDIA uses for describing the language and the set of APIs and all the tooling. It's called CUDA Toolkit. And it's also a kind of a C dialect, and we will later see how that looks like. So how does this work? In CUDA, we kind of get an abstraction. Uh, we write a program that's kind of working on a single thread, but in reality, these threads are grouped into first into group of 32, which is one verb. That one verb is always executing all at once. Like you can imagine the scheduler is or the units in the scheduler are like 32 wide synced execution. So, but this is kind of abstracted away from us for the developer. Uh, in some way, we get a thread ID, and then this would be a trivial program. Get some input based on the thread ID, do some function, and produce some output, and then store it. So that's the kind of the model we use. These threads are grouped into so-called thread blocks. And we have potentially very many of those blocks. Those blocks are kind of split across the GPU, and you can actually have more blocks than fit onto the GPU just at one time. And um, and so it's not like you have to fit your problem exactly onto the GPU, or how many SMs you have and how many blocks can you kind of give to one SM, and limit yourself to that. You can kind of prepare many more blocks, and then basically as the blocks are processed on the SMs, when a block is finished, it kind of vacates from the SM, and a new block gets scheduled there, and so on. So you are able to process more blocks. This is kind of the mapping in CUDA. Single thread could be understood as an NVIDIA likes to call it CUDA core, but this is not not an exact representation. But you can imagine like the like a single SM can have, for example, 2024 active threads at a time. So you can kind of, you could have a block that is as big as 2000 24 threads and or smaller. And yeah, so the threads are grouped into blocks, and those blocks are um, scheduled onto an SM. A block cannot be split across multiple SMs. You can have multiple blocks on one SM, but not the other way. And then there is a kind of logical grouping, which we call grid. This is just basically the uh, if you need, I don't know, 10,000 blocks, then you make a grid of 10,000 blocks, and this is sent to the GPU, and the GPU takes care of distributing the blocks across the SMs. And this is just an example. Let's say you have 8 blocks that you want to execute, and in a GPU with 4 SMs, um, one block per SM, you would do it in 2 waves basically, and with GPU with 8 SMs, you would be able to execute all blocks in just one wave of blocks. Now let's take a look at how a CUDA code actually looks like. Um, so this piece of code here is actually vector addition. So this is point-wise vector addition, just a plus b, c equals a plus b. So this looks like a normal C code. The only funny thing here is this global attribute, which tells the compiler that this is actually a function which will run on the GPU. And this piece, this block ID and block dim, block IDX, and thread IDX, these are kind of a built-in 3-dimensional variables. So each dimension is an integer, and this is kind of used to describe the shape of the grid and the blocks. You can so you can have not just a flat index, but you can have up to 3 dimensions, which is convenient if your problem fits with like multiple dimension, like something like matrix multiplications, for example. You would usually have a 2-dimensional indexing there. So, but the point here is you have built-in variables from which you can compute whatever index you want. These are like the inputs are arrays of floats in this case, and you compute the index, and then you know, and you do it point-wise calculation. So this looks kind of like a single-threaded code, you would say, but in reality, on the GPU, this we could launch a grid of blocks. I don't know, 1 million in size. So you would be computing 1 million of these point-wise operations in one go. Um, and this is the host code. So in this case, let's say n is 1 million. So you allocate first on the host, you allocate the space for 1 million floats for A, 1 million for B and C. Oops, sorry. You somehow initialize them, and not important in our case, in our example. And then you need to also allocate space on the GPU. So these lines here are allocating space on the GPU. So it's also malloc, but it's CUDA malloc. They are the same size. And next, you need to copy data from the CPU to the GPU. So HA is the host A, and DH is the device A, and we are copying from host to device. So we are copying A and B, and then we can go and execute the kernel. This is called kernel, this function. Mm, so we decide we want 256 threads per block. Then we compute how many blocks we actually need to compute all those values based on n. And this, then we call the actual computation. This is kind of a special syntax with those parentheses here. So we are calling this vector add kernel with this shape of the grid. So this is the grid definition, how many blocks and how many threads per block. And as input parameters are the pointers to the device memory we allocated here, and the n, how many we want to compute. So you see this corresponds with this. And after these returns, we need to copy the data back to the host and do whatever we want to do with it. So yeah, this is kind of trivial program uh, that does pointwise vector addition, you could say. Okay, and how much time do we have? Okay, 15 minutes. Now let's jump into the GPU prover that we have. We call it Boojum. Boojum is not only the name of the prover, but it's also name of a library. Um, for you, maybe interesting is that this is Plonkish arithmetization and Fry commitment scheme. So this is a Stark, but the arithmetization is Plonkish, not Air. So it's kind of hybrid, you could say, but it's because it's Fry. I would say it's a Stark. I will try to go quicker over this. So this new proof system is the replacement for our old proof system. Just to give you some idea about the proof system, the old one, it was a snark using Plonk and the BN254 curve. So we had a lot of entities and MSMs, and the amount of data was very large. Like the single polynomial was, I don't remember exactly. I think single polynomial was something like 2 gigabytes, just a single polynomial. And now you have to imagine that the trace is 4 polynomials, and you have to calculate like LDEs for them, and then you know it adds quickly, and so yeah, and you need to store the bases for the MSMs and stuff like that. Um, so the memory consumption was the main problem, and it's also often with snarks memory consumption, and with these large fields, that's usually the main problem. Like I don't remember exactly, but some CPU provers, like for Polygon, I think, or Scroll, they are talking in like about hundreds of gigabytes of memory. And in our case, in our old proof system, we needed GPUs with 80 gigabytes of memory, either one with 80 gigabytes or two GPU. We were able to split it into two GPUs, 40 gigabytes each. Those were A100 GPUs, data center GPUs. So not something like what a regular user would be able to uh, kind of obtain in retail. Um, very big, very expensive GPUs, and they are actually used a lot by the AI folks. So they are also not so easy to kind of get and are expensive. So the goal of the new proof system was to uh, go much lower in terms of hardware requirements. And currently, the new proof system is able to run on GPUs with as little as 16 gigabytes of memory. So your like I mentioned, RTX 4090, which has 24, or 4080, which has 16 gigabytes of memory. I think even 4070, um, and also older generations GPUs, all those would work. So that was a big goal to get this working on your regular gaming GPUs, because ultimately we want to distribute the proving. So you know, uh, we first need to make it possible to run it on consumer hardware. Um, and the other effect of changing to Boojum was the the proof system itself is much more efficient. We use Goldilocks field, which is much faster in terms of arithmetics. Also needs less memory because it's 64 bits instead of, I don't know, 256. Uh, so a lot of savings. Yeah, and so Boojum is currently already running in shadow proving mode, which means the all the blocks we are, or not all, but we are sampling the blocks that we are currently proving with the old proof system, and we are in parallel proving them in with the new one. It's just that they are not published to the L1. We have tools to verify the proofs, but you know, we are just testing and testing them and making sure that we can prove all the blocks we are producing. Um, okay, so what we have, what kind of code and libraries we have. Uh, we have split into multiple libraries. CUDART, CUDART sys. These are kind of just bindings and wrappers around some CUDA runtime stuff. I won't go into detail here. We don't have much time. Um, then the main one I would say is called Boojum CUDA. And by the way, these libraries are all open sourced already. So if you go to Metal Labs on GitHub, there are repositories called always there is prefix era. So Boojum is era Boojum, and Boojum CUDA is era Boojum CUDA, and so on. So yeah, you can look it up. So in terms of functionality in this Boojum CUDA crate, we have entities, bit reversals, Poseidon, Merkle tree constructions, Merkle path queries, simple pointwise operations like additions, multiplications, inverse, and so on, plus some I would say specialized operations like folding for Fry, barycentric evaluation, partial product, which we use for um, for example, copy permutation argument, and so on. We have gate evaluations for those Plonk gates. We have proof of work, which we currently don't use, but it could be used if we want to increase the security. And then something that's called CUB. Um, this is a kind of part of CUDA toolkit. It's a NVIDIA library for functions like sorting, computing, um, let's say reductions. Like if you need to reduce a vector into a single, like do a sum of a vector or a product. So reductions and also scans. scan is just like a generic term, but we are talking about a grand product or grand sum. Um, so this is all covered by CUB. And then we have Shivini crate, which contains the logic itself plus a lot of abstractions. This crate is actually used by a cryptographer to write the prover. So the prover logic lives there, and the cryptographer uses these abstractions and to kind of compose the prover itself. So you can, yeah. Again, we don't have much time, so I will continue. So this is a profiling output. So just to show you how a profiler output looks like, this was actually the MVP, the minimal viable product. This was the first version of the prover we've got. Uh, it had quite a lot of issues, like this blue part here. This is the actual GPU utilization, and we can see that's not very good. We see a lot of gaps, and a lot of functions which are not utilizing the GPU properly, and a bunch of transfers here. These green ones and red ones and from CPU to GPU and back. But the important point here is this was 6.6 seconds. I have split into rounds, which is, I don't know if this the term rounds, it's kind of reference to something you would have in an interactive proof, where you have rounds of going between the prover and the verifier, like the prover making a statement and the verifier making a challenge, and back and forth. So this would be kind of the rounds. Each time a verifier has a challenge, that kind of is one round. So we have first round would be something like transferring the data to the witness vectors or polynomials to the GPU, and doing a bunch of entities and doing an LDE, and then committing using Poseidon hashes. Then would come the second round, where you are computing some arguments for like a copy permutation argument and lookup argument. And then the next round would be gate evaluations. Again, we need to, just to give you concrete numbers, for the fry, we use a blow up factor of 2. But for the quotienting, we actually have blow up factor of 8, because we have gates which go up to, constraint degree 8. So and actually most of the work is done in round 3, which is quotienting, so gate evaluations plus plus those quotient, what's the word? It doesn't come to mind. Basically, we need to add to the quotient also the parts for the arguments we made before, the copy permutation argument and lookup argument. And then last round, I put it into a round, but actually these are many rounds, many fry rounds, you could say. But in this part, we do deep cautioning and then do the fry rounds, and then at the end we do some queries, and that's basically producing all the outputs of the proof. Okay, so this was the first version. Then we need do some improvements and end it up currently with 2 seconds. And you can see this looks much better now. Still, there is room for optimization, but we get a lot of a lot of those transfers. We have still some here and here. I won't go into the detail, but maybe what we did actually. So it turns out that not only is it important to kind of keep the computation running on the GPU, so go as little as possible back to the CPU. But once you have that, you kind of run into other bottlenecks. And in this case, the main bottleneck was the uh, memory throughput. Because the Goldilocks field is so efficient, and we do a lot of these primitive operations like addition, subtractions. It turns out that most of the time is spent actually not doing the calculation, but just moving the data from and to memory, the GPU memory. So the optimization we did was mainly about fusing all these simple operations into bigger kind of pieces of code. So instead of doing for example, the copy permutation argument with these simple operations, we wrote a special kernel for it, which does it in one go, you know. So and yeah, so this is just an example of what we do with copy permutation argument. So this is how the um, partial product constraint evaluation looked like. This is just for one coset. So we are seeing these are thousands of kernel invocations, and it's very inefficient, low utilization, a lot of memory traffic, and we fused that into a single one. And so we did go, when I go back, from 201 milliseconds per coset in down to 11 milliseconds. So, you know, 20x improvement just by fusing those operations together. And there are other parts of the prover like this. I won't go again into details because we don't have the time, but yeah, we optimize those two. And there are still other implementations, like improvements on the table. I will skip those, but yeah, I think we can do another maybe 50% improvement on. Oh, my mic again.
No, we're here perfectly.
Yeah, okay, and this is just an example how the first round could be optimized. Basically, this is some advanced, I would say, implementation where we are able to overlap the flow of data from CPU to the GPU. So those greens are chunks of data being copied, and the blue ones are computations. And what we do, we actually start we transfer the first chunk and immediately start to do entities on it and compute a partial Poseidon hash. Like we don't do the full Poseidon on the whole, but we just let's say take 8 polynomials and do one Poseidon round and store the state of the Poseidon and then do the next chunk in S. So we are able to kind of interleave the copying with the computation. And if you see the time, so if I go back here, the first round was 480 milliseconds, and with this improved approach, it got down to 186 milliseconds. So again, yeah. So this is what we do, Okay, and so that's it. That's it. Okay.
It's super interesting. Thanks a lot for sharing. There are like many like very cool tricks and things that you can leverage to speed up things. It was like really interesting to see. For example, you could like squeeze a lot the fry querying part. So I
Yes,
see the
like
optimization.
the fry query part is basically not even visible. It's a blip in in the overall execution. Yeah. So
Uh,
actually, most of the proving time is currently spent in entities, and we have Poseidon 2 hash, which is very fast. So actually, the entities are more. Uh, it's partially because of the 8 degree 8 blow up in the equation. We need to do LDE factor 8 there.
uh,
So a lot of
yeah,
entities.
and that has to do with the custom gates you're using for Plonk or something
Yes,
like that.
yes. Like it's the Poseidon gate. Like the Poseidon, the non-linearity in Poseidon is degree 7. So
Yeah,
that's where it comes from. We could split it, but that would, yeah, there are trade-offs to that.
awesome.
Yeah.
Does anybody have any questions?
You said the provers and the new ones running in shadow mode right now. Do you know
Yes.
when it's going to be production ready?
Um, I know the plan, but I won't share it. But it's not far away. Like definitely this year, something like 1 month maybe away. Yeah, something like that.
And what would you recommend someone wanting to jump into CUDA or to port algorithms to CUDA
Yeah.
to learn
So the yeah. NVIDIA actually has a very good documentation. So um, when you go to NVIDIA's website, I don't know, you would have to Google like NVIDIA CUDA documentation, and the first thing there you find is the programming guide, and that will guide you, basically explain the architecture and how different things are done, and then goes into like deep details. It's very extensive and detailed. Um, that was my source for like how I gained all the knowledge. So and it's well maintained. So I would say that's the first thing you could read through. And yeah.
awesome. Any other questions? So for me, it was like pretty amazing to see all the optimizations you have in the prover. They are like super interesting. I will try to see and read a little bit the code base to learn more.
Yeah.
It's interesting these fused operations you mentioned for.
Yes, but basically what we are always trying to do, it's a process where you like you are eliminating bottlenecks. like the first bottleneck is obviously this PCIe transfer from CPU to GPU, and the obvious way to get rid of that is to move everything to the GPUs. So that's what we did. But then then you start hitting other bottlenecks, and you take care of those and so on. So
Awesome.
so it's a kind of iterative process.
Yeah, yeah. We more or less have to do the same. So it was like awesome to have you here, Robert, sharing with us all these amazing technology and engineering analysis. So thanks a lot for sharing with the bootcamp. And well, hope to see you sometime later or to discuss with
Yes.
you more on this interesting stuff. So
Yeah, I
thanks a
was
lot.
happy to be here. Thank you, and I hope you had fun.
Totally. Thanks a lot. See you then.
See you. Bye bye.
Bye bye.
Bye, thanks.